Hello again, this is Math 1120, April 14th, Remote Delivery Part 2, and these are the regression comments, and there is a Part 3 that deals with contingency tables. This is from Sullivan Chapter 4. So recall from the videos that the response variable is the y, an explanatory variable is the x, and a scatter diagram is we plot the values of the ordered pairs for each individual, and the explanatory variable is plotted on the horizontal axis, that's the x, and the response is plotted on the vertical axis, that being the y. When we do that, we can recognize that there are patterns that indicate a positive linear slope, a negative linear slope, and perhaps something that's not linear at all, or maybe even no relationship. As you learned, the correlation coefficient, or Pearson correlation coefficient, is a measure of the strength and direction of a linear relationship between two quantitative variables. The Greek letter rho represents the population correlation coefficient. R represents the sample correlation coefficient. And here is the formula for the sample correlation coefficient, and here is what all of those variables mean. And this was discussed and derived in the video. Now this is an additional computational formula that some students find useful in computing this. In a sense, even though it looks more complex, it can be somewhat simpler to compute this way. So this measures how strong and in what direction the relation is. Now these are properties that were all in the video. The correlation coefficient is always between -1 and +1. If it's 1, that means it's a perfect positive slope. If r is equal to -1, it's a perfect negative slope. The closer r is to +1, the stronger the evidence of a positive slope. The closer r is to -1, the stronger is the evidence of a negative association between the two variables. If r is close to 0, then little or no evidence exists of a linear relationship between the two variables. And outliers can strongly affect the correlation coefficient. The correlation coefficient is not resistance. Now this is something that was not in your video, and that is determining if the linear relationship is strong enough to declare that the one exists. So step 1 is you determine the absolute value of the correlation coefficient that we just discussed, and then you look at the critical values in table 2 from appendix A for the given sample size. We will show you that, and here is the decision. If the absolute value of the correlation coefficient is greater than the critical value found in the table, we say a linear relationship exists between the two variables. Otherwise, no linear relationship exists. This is what table 2 looks like. You can see there's a column saying how many data points you have, how many ordered pairs you have, and this is the value of the correlation coefficient. Again, we take the absolute value of the correlation coefficient and compare here, and this is the breakpoint between a linear relationship existing or not existing. In some of your videos, I think some of this will continue in the videos that you're looking at now for this coming week, but a linear correlation coefficient that implies a strong positive or negative association does not imply causation if it was computed using observational data. There's another way that variables can be correlated without there being a causal relationship, and that's what we call a lurking variable. A lurking variable is related to both the explanatory variable and the response variable. For example, as air conditioning bills increase, so does the crime rate. Does that mean that folks should turn off their air conditioners so that the crime rate decreases? Certainly not. In this case, the lurking variable is air temperature, and as air temperature rises, both air conditioning bills and crime rates rise. In the video we did discuss the least squares regression criteria. The least squares regression line is a line that minimizes the sum of the square distances or errors. It's the best line that we can draw, and in a lot of literature and certainly in your book they call this Y hat. So here is the formula for the least squares regression line. This was derived again in one of the videos that you watched. And so it is y hat equals, this is m, the slope, except we're calling it b1, times x plus b0. And this is one formula for b1, but here's an equivalent formula down here. And so these are the formulas that you learned in the video. And what you can do is you can solve this equation for b0, and you get that this is going to be y0 minus b1 x bar. So this is y bar minus b1 x bar. And so this ends up giving you the y-intercept of the least square regression line. And x bar is the sample mean, and so on and so forth. This defines what all of these expressions are. And you were warned not to do extrapolation in the video, and here the way Sullivan says it is, be careful when using the least squares regression line to make predictions for values that of the explanatory variable that are much larger or much smaller than those observed. Things could change and be different. The last thing that I think I'm going to talk about here is called the coefficient of determination, r squared. And this is capital R squared. This measures the proportion of the total variation in the response variable that is explained by the least squared regression line. It sort of says another measure of how good does it fit. And the calculation for a two-variable linear fit is that capital R squared is equal to lowercase r squared. And again, regression lines are not resistance. An outlier can be very influential and change this, so the analyst must be careful about outliers. Let's do an example now. This is a problem from your chapter test, actually, and it's a good problem because I think it covers almost everything that we talked about here. So crickets make a chirping noise and so on and so forth. So somebody, these guys down here actually, the researchers, measured the temperature, X, and the chirps. And they ask a whole bunch of questions. So we'll go through and answer each one of these questions. So it says, what's the likely explanatory variable in this data and why? Well, clearly, the chirps that the crickets are making is not raising the temperature outside. So the temperature is going to be the explanatory variable because it influences the other one and not the other way about. It's not always that clear, but that's what happens here. They ask us to draw a scatter diagram of the data. And here's what the plot will look like for y as the vertical axis and x as the horizontal axis, and these are the 15 data points that we have. The next question is, we were supposed to compute the linear correlation coefficient between temperature and chirps per second. So we use this data and do the calculation, and we find that lowercase r is equal to 0.835. Now that's positive, so that means it's a positive association. As the temperature goes up, the number of chirps goes up. That's somewhat close to 1, but not so much. And in fact, if you were to square this, you would say r squared is 69. It's 0.697, which means that 70% of the variation was explained by this regression equation, but not more than that. Let's see. Does a linear relation exist between temperature and chirps per second? Well, we have to take that number that we just found, that 0.835, and we have to look at the table. And we had 15 data points, so the cutoff is 0.514. That means if the absolute value of 0.835 is bigger than this, then a linear relation does exist. So the answer to this question is yes. I would ask you to explain why using the values from the table. Here the question is asked to find the least squared regression line treating temperature as the explanatory variable and chirps per second as the response variable. If we work through the calculations, we get this. The y-intercept ends up being minus 0.309, and the slope ends up being 0.2119. And here again, you can see that r squared is what we get if it was little r squared, and that is 0.697 or 69.7%. That is almost 70%. Interpret the slope and y-intercept if appropriate. The slope tells you that for every increase of a degree in temperature, the number of chirps increases by 0.2 and change. The y-intercept is negative and really doesn't make sense in this case because the temperature does not go to 0. In D, they ask if a cricket chirps 15 times per second when the temperature is 82, is this above or below the average at this temperature? Well, we're going to take the average from the least squared line. And, oh, excuse me, I skipped one. We wanted to predict the chirps per second if it is 83.3. We're going to deal with both of these at the same time, C and D. And so I use my equation. Here I have the slope and the slope here, and this is the intercept. So if I plug 83.3 in, I get 17.34 when I do the calculation. If I plug 82 in, I get 17.0668. So 15 is under that value. Question E says, if it's 55 outside, should you use it? And the answer is no, because that's way outside the temperature range. I bet that the crickets are all hibernating at that time, and this would be useless to use that. And then it asks us to compute and interpret r squared. We've already done that, and we got it was 69.7%. That means that this regression equation explains almost 70% of the variation. The remaining is other factors. This is the end of part 2.